All right, guys, so we're going to start topic 10, beam deflection, which is, this is going to be the last topic that I post. And if you got these slides from Titanium, make sure you download them after this video is posted because I changed the slides a little bit. I added some information, took out some unnecessary information. So just so that we're all using the same slides, make sure you download them now. Okay, so another quick note, actually, you'll see that these are, or this topic is about 80 slides long, so don't be worried about that. We're not going to go through all 80 slides. We're going to go through the important slides. Let me get rid of this text box. Sorry. We're going to go through the important slides here, okay? We don't really have enough time to cover all of these methods of deflection, so I'm going to kind of just go over the ones that you're going to see on your final, and we'll kind of just go from there. Okay, so what are we going to discuss for beam deflection? We have all of these different methods that we can use to calculate deflection of beams. And this is a super important topic because it kind of leads directly into structural analysis. So you'll see that when you get into structures, to some extent, you'll kind of pick up where this class left off. And what we can do with these methods of deflection, in addition to finding deflections and rotations, is actually use these methods to solve for indeterminate structures. So you'll see here that's kind of like point 2, and we're not going to actually get to cover this in this class. So I'm going to write here, and I put this in the slides later on, but this is an extra topic. Okay, and you'll see me skipping a lot of slides in this, and that's just because I don't want to cover extra information that we don't have time for. So I'm kind of going to cover what's going to be on your final, which is kind of a hint, or I'm just kind of straight up telling you guys. Okay, so here we're going to start with first understanding what the elastic curve is and understanding what deflection and rotation is. Because I know those words are sometimes words we commonly may use, but what do they actually mean and what do they represent in terms of a structural system? So before we get into calculating these actual values, what do they mean? The first thing we need to know is what the elastic curve means. Whenever you see the elastic curve, this is going to be somewhat of a representation of the deflected shape of your structure. Okay, and when you get to structures, you'll be asked a lot to draw this shape. So it's good to start recognizing what those support reactions mean again and how you can draw what's happening in terms of loading. Okay, so let's take a look at this beam over here and let's define some things. So we see that the beam has this horizontal axis, okay, and this blue curve, this is the deflected shape due to that force P. So the beam has deflected some shape due to a force P, and this, if we're looking at, let's say, just this point on the beam, this here, this distance, it's a distance, this is our deflection at that point. So you can see that deflection, just like shear and moment, varies depending on where you're standing on the beam. So deflection, we use a couple of things to determine, or to a notation in terms of deflection. We can call this Y, as you can see, because it's in this vertical direction for beams. You'll also see it as delta, and you'll also see it written as this fancy little V shape. So whenever you see this fancy little V shape, I'm going to always draw these two little tails on the V so that we never confuse this with shear, because sometimes that gets a little bit confusing. But any of those, they just mean deflection, all the same, just different notation. Now, in terms of rotation, let's look at the rotation at point A. So how do we figure out the rotation? Well, we draw a tangent line, okay, and then we draw the tangent line to the original shape, and we see that there's some angle that it's changed by, and this angle theta is the rotation. Okay? You can see here, point A has rotation, but point B does not have rotation. This tangent line is the same, so theta is 0. But that makes sense, right? Because this is a fixed support. And we know at fixed supports, we cannot rotate. So it's forcing that beam to stay steady there. Okay, so you want to kind of think about those things when you're drawing this elastic curve or drawing the deflected shape like this. Okay, and again, one of the most important applications, of course, in addition to determining deflections, because those are also very important, especially when we're designing, which is not often, but when we're dealing with brittle material. We do design with concrete a lot that's brittle, but we kind of reinforce it with steel and do a couple of other things to mitigate that brittleness. But we don't necessarily design an entire building with glass and no other support. So it's not as common, but we do definitely need to limit our deflection for structural integrity purposes, but also because deflection helps us figure out how to analyze an indeterminate system. And we'll talk a little bit more about this. You'll definitely talk more about this in structural analysis. Okay, so let's continue talking about the elastic curve here. Basically, the elastic curve is not difficult to draw in general. And what we can do is, if you do have a structure that is more challenging to draw and you don't really know how the loads are going to affect the system, what we can do is we can use the moment diagram to construct the elastic curve. And I'll show you how we can do that with this example. Okay, so we have a beam here, and it has two loads placed on it, P1 and P2, and we have a roller and a pin. So let's say we're going to draw the moment diagram for this system. Okay, we'll have, of course, starting with 0 moment, ending with 0 moment, no moment applied here. Let's draw some vertical lines. Okay. And what happens here is we have some value of moment that shifts to this point. We have some value of moment that would shift to this point, and we would have to have this come back and close at 0. And this is our moment diagram. And a couple of things that we can note here. We can note that this whole area is negative, and that this whole area is positive, right? So what we know about the elastic curve here, which is the shape, this deflected shape, we know, let me continue drawing these lines here. And then we have some important points C and E that are already drawn for us. So what we know about this, if black is our original line, right, we have a roller support here. The black line is our original beam. We have a roller support here. We have a pin support here. Draw it in blue. We know that at P1, we're going to definitely deflect downwards some, I'm going to call this delta, right, the deflection. We're going to experience some delta A here. It's going to definitely push down at A, and it's going to move down, okay? We know that we're going to have 0 deflection at the roller and 0 at the pin, because that's the definition of a pin and a roller. We can't move, okay? And what the other thing that we know is whenever our moment diagram is negative, that means our elastic curve is concave down, which is like a frown. And whenever it's positive, that means that our elastic curve is concave up, like a happy face or a cup. Okay, U up and then down like a frown. Okay. So all we have to do, if this is concave down, that means from here to here, I definitely have to have concave down. And the reason I've drawn C here is because at some point here, we know that it changes and it goes to concave up. So we call this point C some kind of inflection point. Okay, we have some kind of point where it changes from this concave up to concave down. And that's generally this elastic curve. Okay, we can do the same thing with this beam here. So we can start by drawing the moment diagram. We're going to have some negative moment here. It's going to be pushed up. And then no change here, and this rotation back to get it down. And here we have negative, here we have a positive. So when we come to draw our elastic curve, again, this was a fixed support, so this is where it's really important to first start with the support. If this is a fixed support, we know for sure that for some portion, we're going to have 0 rotation and 0 deflection. We have no support here, so we know for sure we're going to get some change, some delta C. If we start off, I'm going to draw a little line here. Okay, we know we have to be some kind of concave up like this, down first, sorry, down like this, and then we're gonna go some kind of up here and something like this, okay? And so we just have to remember that we have no delta or theta at fixed supports. Okay, there's no support at C, there's nothing stopping it from moving, so we definitely have some delta there. Okay. Okay, so we've already talked about this concept of moment curvature when we were deriving the bending stress formula. So I'm not going to go into this anymore right now, but I will let you review these slides again. But they are the same, it's exactly the same thing that we derived all for bending stress. So if part of this doesn't look familiar, go back to the bending stress topic and review it. But for the sake of time, I'm going to kind of skip through this and get to the point. So what we can do is we can actually determine slope and displacement through integration when we get down to this formula here. Okay, and just to be very clear, this is actually, let me scroll up here so I can show you what's happening. This value of deflection, they're using this V here, okay? This V, this little V. I'm gonna either use delta or Y to make this a little bit easier so that you don't ever confuse it with shear, but the book does use this little V, so all of these equations that are copied from the book are going to have a little V. And if you're reading the book, it's going to have a little V, so just be careful with that. Okay, so here I'm going to go until we get what we're looking for. So this is the big picture here. This is what we're going to use to solve for our slope and deflection. So if you go through this derivation, what you'll see is from our moment curvature relationship, we can actually determine our slopes and deflections through the load, the shear, and the moment. So we can use the shear, the moment, and the load to actually take the derivatives and find our deflections and rotations, which is really cool. Okay. So in terms of sign conventions and coordinates, basically, we're going to use the same sign conventions that we had previously used when we're deriving these formulas, and this is super important when we're doing this because we all want to make sure that our signs are appropriately reflected on our diagrams so that we're getting answers that match up. Okay, let's talk a little bit about boundary conditions. So this is very important regardless of what method you're using and in a lot of applications. So these need to be, you can memorize them, you can remember them, or you can do whatever you need to do so that this is kind of ingrained in your mind. The first one we're going to talk about is the roller support. And generally a roller support, this is a review from statics a little bit, but generally a roller support is drawn like this. And what we know about a roller is that there's no deflection that can occur in the Y, 0, but we also have no moment resistance. I'm going to shorten this as NMR because I'm going to write that quite a bit. And then we also know that theta cannot equal 0. There has to be some rotation because it can rotate. Okay? Now, number 2, we have the pin support. Typically, a pin is drawn as a triangle. We know that we have delta Y is 0. We can't have a delta X either. We have no moment, I keep putting in our no moment resistance. And we know that theta can't equal 0. Okay, next we have fixed supports. We typically draw that as a straight line like this. We know we can't move in the X, we know we can't move in the Y, and we know that we can't rotate. Okay, pretty easy. Room here. Okay, the next one we have, number 4, is a free end. So a free end basically means it has no supports. We have no shear resistance, and we have no moment resistance either. Okay, and the last one we'll discuss is the internal hinge or internal pin or a hinge. It's called both of those things. And that looks something like this, a little circle in a beam. And all we know about this is we have no moment resistance. Okay, so remember these when you're solving problems. This will help you a lot in determining the elastic shape, the elastic curve, the deflected shape, and it'll help you in your future classes too, for sure, for structural analysis as well. Okay, so let's get into an example now. We have a simply supported beam and it's subjected to this concentrated force that's shown, and we want to know what the maximum deflection of this beam is. Okay, so the first thing we're going to do is let's draw the elastic curve here. And I'm going to show you how we can do that without having to draw the moment diagram when it's a simple loading like this. So at point A, we know that we can rotate, but we can't have any deflection. That means that it has to stay there, but I can have some rotation. Same thing for C, I can rotate. So I'm just going to connect those, something like this. Okay, and this here is my elastic curve. Okay, pretty simple. Now, we can see that our moment function changes at point B. So we're going to have to make two cuts here to figure out what M is. Okay, because we're going to actually, let me scroll back up here. We're going to be plugging into these formulas here. Okay, so because of that, we can see we need MV and the load, which we already have the load. Okay, so we're going to make two cuts here. So let's do this here. And when I make that cut, I'm going to draw these with this positive sign convention, some M1 and V1, and I'm going to call this X1. And I have no load on this. So you can see here that M1 is equal to 2X1. Okay, and now our cut number 2. Our moment changes after the 6 kilonewton load is applied. So here's my cut 2. I still have a 2 kilonewton. I have 2 meters until I apply the 6 kilonewton load. I'm going to have some V2, some M2, and I'm actually going to call this entire part X2. And if I solve for M2 here, I get 2X2 minus 6 times X2 minus 2, and I end up getting this equation M2 is 4 times 3 minus X2. Okay, now I can get into my slope and elastic curve. So I'm going to use my moment 1, which is defined from x1 till 2. And you can go back and see those equations. I'm going to use d squared delta 1. I'm going to change them from v to delta because I don't want to confuse it with shear. I know that's equal to 2x1, just so we know v is equal to delta, this little v. And I'm taking the integral. So once I take the integral of both of those, I end up getting this. And I can take the integral again to get EI delta 1 equals 1 over 3 x1 cubed plus c1 x1 plus c2. And I have now an equation in terms of delta 1. And I can do the same thing for my moment 2, which is defined between 2, x2, and 3. And I have EI d squared delta 2 over d x2 squared is equal to my moment function. I can take the integral and I get not d squared, d delta 2 equals 4 times 3x2 minus x2 over 2 squared. And then I have plus another constant of integration. And then I can take another integral, and I can get EI delta 2 equals 4 times 3 over 2x2 squared minus x2 cubed over 6 plus c3x2 plus another integration constant. And now what do I have? I have equations, but I have all these constants of integration that I need to now deal with and solve before I can do anything. Okay, so how can I solve for C1, C2, C3, and C4? I need to evaluate these using boundary conditions. What do we know about boundary conditions? So we go back to our problem and we say, well, I know a couple of things about this beam. I know that at x equals 0, my deflection has to be 0. And I know that at x equals 3, my deflection also has to be 0. And this deflection, the x equals 0, falls within x1, and this falls within x2. Okay? I also know a couple of other things. We call these, so these are our boundary conditions. Okay. I also know some information about my continuity of the beam. I know that, so I'll say one continuity condition. I know that the derivative, this d delta 1 over dx1, has to be equal to d delta 2 over dx2 when x1 equals x2 equals 2. At that point too, I know that this has to be continuous, right? Whatever happened before has to happen after. And I also know that my delta 1 has to equal delta 2 at this x1 equals x2 equals 2, because it has to be a continuous piecewise function. I can't have a break there or it's not a function. Okay, so now I'm going to use this information to come back. I'm going to use all of this information to solve for constants of integration. Okay, so let me come back here and plot. Let me see how much room I have left so I can ration. Okay, so I'm going to come back here and I'm going to say, well, delta 1 equals 0 at x1 equals 0, and I'm going to plug that into the first equation, and I get all zeros for C2, so I get C2 equals 0. I also know that delta 2, this was delta 1, equals 0 at x2 equals 3. And if I plug that into the equation, I get 4 times 3 over 2, plugging in 3. And I can't really solve for anything here. I have a C3 and a C4, but now I can say that d delta 1 over dx1 at x equals 2 is equal to d delta 2 dx2 at x equals 2. And if that's the case, I can plug both of those in and equal them to each other. And now I have C1 and C3. Can't solve anything there, but I can also plug in this. So it's just a system of equations now. And I have to see what I can use to solve for all 4 constants. Plus C3 times 2 plus 4. And if I solve all of these equations, I get C1 equals negative 8 over 3, C2 equals 0, C3 equals negative 44 over 3, C4 equals 8. And now I want to plug these back in to my equations so I can get my complete equations here. Excuse me. Okay. If I do that, I get EI d delta 1 over dx1 is equal to x1 squared minus 8 over 3. And EI delta 1 equals 1 over 3 x1 squared minus 8 over 3 x1. And now for number 2, EI d delta 2 over dx2 equals minus 2x2 squared minus 44 over 3. Okay, and if I wanted to find the max deflection, which is what the problem asks for, I need to remember that max deflection occurs when slope or derivative equals 0. So basically max delta occurs when d delta dx equals 0. So I just need to set that equal to 0 and figure out what that number is. So here, I'm going to take my delta equation, x1 squared minus 8 over 3 equals 0, and I get x1 equals 1.633. Now I have my other delta equation, which is right here. Let me see. I'm going to do it with both of them so I can figure out what the right answer is, right? So 12x2 minus 2x2 squared minus 44 over 3 equals 0. If I do quadratic equation here, I get x equals a negative 3.667 and I get a 9.667. Neither of these numbers work. Take out the negative. The other one doesn't work on our beam because it's less than that many meters. So I'm going to pick the one that works here. If you have multiple that work, you can plug them in and just solve for your max deflection. Okay, now I'm going to plug this back in. I get EI delta 1 equals 1 over 3 times 1.633 cubed minus 8 over 3 times 1.633. And I get negative 2.90 over EI kilonewtons meters cubed, and the negative means that it's going downwards. Okay, and that is my answer for example 1. Okay, so example 2, you're using the same method and applying it to solving for the deflection, the displacement deflection. I'm not going to go through this and solve it because it's like the first one, but you guys can try this one on your own and make sure that you get it. All right, so the next method that we're going to go over to solve for slope and deflections in this class is called the conjugate beam method. And the nice thing, or the advantage kind of using the conjugate beam method to solve for problems, is that you get to use just your knowledge of statics to solve for slope and deflection. Okay, so instead of having to basically go through the steps that we went through previously and solve for slope deflection equations, we get to just use concepts actually of shear and moment diagrams to solve for slope and deflection. Which is pretty cool. Okay, so let's talk about how we connect this concept of shear and moment diagrams to slope and deflection. And I'm going to use this blank page, but I also have screenshots from the book here for you to follow along with and kind of summarize what I'm going to write up here. All right. So here is the connection that we're trying to make when we're using the conjugate beam method. Okay, we need to kind of tap back and recall that the derivative of the moment diagram, dm dx, the derivative of the moment diagram, is equal to the shear diagram. Okay, and along with that, the derivative of the shear diagram is equal to the loading on our system. Okay, and then we can further connect this and say the second derivative of the moment is then equal to that distributed load that's applied on the member. Okay, and what we can do here now is we're going to set up a relationship between what we're talking about up here with shear and moment. And also moment curvature, which we discussed previously. So shear and moment, I'm going to re-summarize these points down here. We have dv dx equals w, and we have d squared m over dx squared, forgot my squared there, equals w as well. And when we're discussing moment curvature, we have d theta dx, which is the rotation, which is equal to m over ei, moment curvature relationship. And then we have the second derivative of the displacement with respect to x, which is also equal to m over ei. So there's this similarity that exists with the way that we can represent moment curvature and shear and moment. Okay, so the idea here, and remember, I'm going to kind of write this throughout. Remember that whenever we use y, that's the same thing as using delta. That's the same thing as using this fancy little v or nu. So when I put y here, it's the same thing as delta or nu, kind of in reference to whatever you're using to study, either the textbook or these notes. These are all the same thing. They're all symbols for deflection. And that would be in inches or millimeters. Okay. So back to this relationship. What we see here is we have a first derivative and a first derivative. We have a second derivative, a second derivative. Okay. So what we want to do here, so where things get kind of interesting, we want to say, okay, so if I have loading and I apply it on a member, I can solve for the shear V and the moment using calculus concepts, right? Using the shear and moment diagram pretty simply. Well, what if I took the loading and instead of making it W, what if I took m over EI, moment curvature, and I applied it as loading on the beam? So as W, then if m over EI is my new W, my new loading, that means that the derivative of this as my load would actually equal this, and the second derivative of that would equal this. So getting my shear and moment diagram of m over EI would really give me slope and deflection, okay? So we can look at this also from the integral perspective. We have v is equal to the integral of w dx. We also have theta is equal to the integral of m over EI dx. We have moment equals the double integral of the loading dx, which is similar to y, which is equal to the double integral of m over EI dx. Okay, so all we have to do is apply m over EI as load on our beam, then solve for shear and moment, and then my shear and moment would correspond to slope and deflection. I'm going to skip around for a second here to show you what the two theorems are. So that's why theorem 1 and theorem 2 of the conjugate beam method, we see the slope at a point on the real beam is equal to the shear at a point on the conjugate beam. What is the conjugate beam? The conjugate beam is almost like a fake beam, okay, with m over EI applied as the loading. Okay. So my slope corresponds to my shear, my displacement corresponds to my moment. And the minute you see this in an example, it becomes super straightforward. We just have to draw, here are kind of the steps before I start with the supports. Let me kind of draw some steps for you here. So the steps here will be 1, draw V and M diagram for beam. 2, apply M over EI. EI is just a constant, so you're really just applying the moment diagram. You're really just applying the moment diagram. And 3, solve again for V and M on conjugate beam. What's a conjugate beam? This is my conjugate beam. Okay. Now we have to talk about supports. Okay. So when we're dealing with beam supports, this is super important. Our conjugate beam and our real beam have different supports, sometimes, not all the time. And that's because we need to think about this now in terms of slope and deflection, not in terms of necessarily just shear and moment. So, for example, if our real beam has a roller, draw a roller here for you. Let's say we have a roller right here. Okay, this is our real beam. Okay, if our real beam has a roller here, we know that a roller means that we can not displace up and down, so 0 displacement. Okay, and we know we have a non-zero slope, so we can definitely have some type of theta, some slope there. Okay, now on our conjugate beam, remember now, conjugate beam, we need to think about what would be happening here in terms of slope and deflection as well. So because we have 0 displacement, 0 deflection, we also need to add a pin or a roller to be consistent. Okay, because remember here, our slope is like our shear, our displacement is like our moment. Okay. Now, this is where things get a little bit trickier. If our real beam has a fixed support, okay, this means that our slope and displacement are 0. Okay, that means slope, theta is 0, y is 0, no displacement, and no rotation, which means that on our conjugate beam, this is the real beam, on our conjugate beam, this needs to now be a free end. Okay. So here is a table that you can use as a reference. All you have to do is look at what your real beam has to offer. Okay. And then you can convert it to a conjugate beam by just switching up the support appropriately. So for example, let's say your real beam is given like this, fixed support and a free end. You'll go to the table and you'll say, okay, well, I have a fixed support here, so that fixed support needs to be changed to free. So I'm changing the fixed to a free, and I have a free here on the real beam, this is the conjugate beam, that needs to be changed to free, needs to be changed to fixed. So that's how I switch it up. Okay, and we'll do a couple of examples so that you can see how this is done. Oh, here are some examples of going from a real beam to a conjugate beam. These are kind of grayed out because we call these kind of like the fake beam. This isn't the real beam. We're just using this beam to get some information. Okay. We're going to go ahead and go through this example here so that we can understand basically exactly how to implement the conjugate beam method and what that kind of looks like. Okay. Alrighty, so we need to determine the slope and deflection at point B of the steel beam, and the reactions have been computed already for you here, 5 kips going up, 75 kip foot for the moment, and we have an E and an I value. So the first thing you always want to do is you want to draw the shear and moment diagram of your beam. So this is kind of step 1, shear diagram. And of course, this is super important, our moment diagram. Okay. And here we're going up 5 kips. No change. Down 5 kips. And then nothing. Here for moment, you can see we have this negative 75. Let me draw a line here. We'll pretend that line intersects in the right way. Okay. And then we're going to go up here. That's pretty much it. And now what we're going to do is we can construct our conjugate beam. So here, all we have to do, this is the most important thing. If this A was a fixed support, it's now free. B was free, now it's fixed. You're just going to do that from the table. Okay. And now the load on our new beam, this is our conjugate beam. Let me write that here. The load on our conjugate beam is just going to be whatever you see on the moment diagram. And I'm drawing it going down negative, just like I would on some real loading. This is a triangular distributed load. Negative 75, right, going down. But it's going to be 75 over EI, because that's that moment curvature relationship. Okay? And now all I have to do is analyze this when I get, so here, this is the conjugate beam. So V of the conjugate beam is equal to the rotation of the real beam. And then M of the conjugate beam is equal to the displacement of the real beam. This is that delta value. Okay. So now this is going to be a quick analysis here. Let's do this. So we have our resultant here. This is still 15 feet right here, 15 feet, 15 feet. We need to calculate our shear for the conjugate beam, our moment for the conjugate beam. Okay, and we can sum forces in the y direction, set them equal to 0. We get negative 562.5 over EI, that's this here, minus VBC equals 0. And we end up getting VBC equals negative 562.5 over EI equals negative 562.5. Now let's plug in 29 times 10 to the 3 times 144 for the conversion times 800 inches to the 4th times 1 foot 4th over 12 inches to the 4th inches to the 4th. And that equals negative 0.00349 radians, and this is theta at point B on the real beam, because it's the shear on the conjugate beam. Now we can do the same thing. We can sum moments, and we get 562.5 over EI times 25 plus M conjugate beam B equals 0. We get the moment at point B on the conjugate beam is 140. 140. 62.5 over, this is in KSI, again, same conversion, and we get 800 divided by this 12 to the fourth, and we end up getting negative 0.087 feet. And this goes to now delta B, convert to inches, and we get negative 1.5 inches. It's negative because the slope of the beam was measured clockwise and the displacement is downward. That's why we have these negative values. So this is clockwise, this is downward, which makes sense. Okay, so I'll post one more video with the next example, but for now, let's make sure that you guys understand this part and that you're good to go before we move on. Okay, so this video is going to go over another conjugate beam example so that you have more than one to go off of for your final. And this particular example is a little bit tricky, so I want you guys to pay close attention to it. And I'm going to kind of explain it before we kind of jump into solving it. So the idea with conjugate beam analysis is, if you remember from the previous example, you have to turn the moment diagram essentially into the load on the beam. Okay, that's all you have to do. Draw the moment diagram and then make the moment diagram your load. But you can imagine what happens when you have like a super complicated moment diagram. It starts looking crazy on your beam and you can't even analyze it because it's not from those basic static concepts that we know. So you always want to make sure that you're not doing anything more than a triangular distributed load, a constant distributed load, point loads, and things like that on your beam. Because then it's just not realistic, and then conjugate beam method wouldn't necessarily be the best method to use. So I'm going to show you now what we can do to make sure that our loading is still simple enough to kind of solve and put together. So what we want to do for this example here is we're going to separately analyze the 8 kip load, the 30 kip load, and the roller support at C, okay? And that way we'll be able to kind of make this loading on our beam look a little bit better, okay? So the first thing here, let's draw our shear and moment diagrams for this member. Okay, and what I'm going to do, I'm actually going to draw the shear and moment diagrams split up for each of those loads here. So let me get to that here. I'm going to come, where should I put this? Okay, actually, let me go like this. Okay, we'll say that this here is equal to just my beam with the 8 kip load, okay, plus my beam with the 30 kip foot moment. And of course, let's not forget this little hinge here. We have a little hinge. Plus my beam with some reaction here, CY. Okay. And this makes this a determinate structure that I can solve instead of one that has 4 unknowns that I'd have to kind of pull that hinge apart to solve for. Okay. So the first thing I want to do is I want to solve for the unknown reactions at all of these points for this, this, and this for each system here. Okay. And what I'm going to do actually first is I'm going to come here, and if I were to analyze this system, I need to figure out what this CY is so that I can put it here as a reaction force. So in order to figure out what CY is, I'm going to have to pull this member apart first. So I'm going to say that I have this beam here attached to this beam here. Here I have a CY. Here I have an AX, an AY, an MA. And then here I've exposed equal and opposite bx. And I'll say here, actually, let me draw this a little bit better. Oops. We'll call these by and bx. Okay. And I'm going to put back my original loading for now. Okay. And I'm going to analyze both of these sides in order to get my reaction. So I'm going to say sum of moment at point B has to be 0. Counterclockwise is positive. So I have a cy times 15 minus 30. And I get cy equals 2 kips, which is what I needed for this. Okay. So here I'm going to replace this cy with 2 kips. Okay. And I'm going to solve now for the moment values or the moment diagrams for each of these loads. So I'm going to come here and I'm going to call this 1, 2, and 3. So let's start here with 1. Okay. Now here we just have a cantilever beam, and what we have is we have some AX. We assumed here we'll say AY, and we have some MA. We can already see that AX is equal to 0. If we sum forces in the Y direction, we can see that AY equals 8 kips. And let's say we sum moments about point A, set them equal to 0, counterclockwise is positive. The 8 kips acts 12 feet away. We end up getting negative 8 times 12 minus we get MA is equal to 96 kip feet, but in the opposite direction, so counterclockwise. And this is for case 1. Okay, now let's do the same thing for case 2. Okay, here we have case 2. Actually, we should draw let's draw the shear moment diagrams for this before we do that. Okay, it's probably a better. So here, for this beam, we have 8 kips, and we have so we have shear diagram. Basically looks like that. And we have a moment diagram, which this is the important part. We'll put it all together later. Our moment diagram, which basically comes here. We have negative 96 up until this point. And this is M, and I'll put M1. This is very important here. Okay, now let's do this for case 2. Let me copy case 2. Okay, and again, now we can solve for, let's do the same directions here. AY, AX, MA, and this is just for the 30 kip now. So we're going to see that here we actually have an AX value, which is 0 from sum of forces. We're going to sum moments around point A, set them equal to 0, counterclockwise is positive, and we get, basically we can see MA is equal to negative 30 kip feet. So again, it's going to be the 30 in the basic, I'm going to take out the negative here and just write 30 counterclockwise. And this is for case 2. Okay. Okay, so we have no shear for this part, and we do have a moment diagram that's constant. It's going to be M2 at this 30, goes down 30, and then just goes up by 30. Okay, so we have 1, 2, and then now we need the third, which is for this CY of 2. Let me copy this here. Once again, we have our AX, AY, MA. We're going to say that AY now is equal to negative 2 kips. It should be going in the opposite direction. AX equals 0. Sum of MA equals 0. Counterclockwise is positive. Negative MA plus 2 times, what was the length? 15 plus 24 equals 0, and if we solve all of this, we get MA equals 78 kip feet. Okay, and we put it in the right direction already. And so last thing we're going to do here is again draw that shear diagram. We see here we go up to 2, nothing, down, and then here our moment diagram should be should be linear. We're starting at 78. We're going to end at 0. And now we have, this is M3. And I forgot actually the over EI, of course. Okay. Now we're going to combine all of these three. Combine all moment diagrams as loading, and this is our conjugate beam. So here is our beam. Let's add all of our loading on there. So the first load we have the, what was it, negative 96. So I'm going to draw that probably this direction. The second one is the negative 30. I'm going to put it up here. It doesn't matter if you put it above or below as long as you draw it going down. So they have, the arrows are what matters. And this is going to be the negative 30 over EI. And the last load we have on here is the positive 78. And so we have something like this. And this now is our conjugate beam. And so that we know all of the dimensions here, we have from here to here 12 feet. Then we have another, let's say 12 feet. Sorry, these dimensions are obviously off. They're actually really off because this is supposed to be 15 feet. But you get what's happening. Okay, now that this has happened, we finally have everything we need to determine our slope and deflection here. So let's go back and see what we're looking for this problem again. We want the displacement of the pin at B and the slope of each beam segment connected to the pin. So we want delta B, and we want theta B from the left and theta B from the right. That did not look like an R. Right, there we go. Okay, so let's come here. And the first thing we're gonna do now is we need to basically sum forces just to the right of that point B, which is, let's see where point B was on this beam, at 24 feet. So this here is our point B. So what we're gonna do is we're going to, I'm gonna put all this in green. Okay, so if I do that, I need to get all the resultants of these loads. So here's the triangular load, here is the 30, and basically what I have here, I have 225 over EI. I'll have this 3.6 over EI, and I'll have, 450. And here I've exposed a VB prime to the right and an MB prime. And now I can sum these forces, and I can say VB prime R plus 225 over EI minus 450 over EI minus 3.6 over EI equals 0. And now I can solve for this theta value. And I can get theta is equal to, okay. Now what we want to do is we want to figure out this is the rotation. So we need to figure out now the displacements for each side. So let's continue with the other side. And get all of our resultants for this side. This is the resultant of the 30 down here. And then on this side, we're going to have the VBL from the left side and the MB from the right side. Now we can sum our moments here. And then basically the internal moments now at B prime have to be the displacement of the pin. So because that's what we know about the conjugate beam, that was part of our theorem. So we can say now if we plug in EI, displacement at that point is negative 4.58 inches. And then if we sum forces just to the left of B, we get this VB prime L plus the resultant so we're just adding all those resultants, and we can get theta B to the left equals VB prime to the left equals 0. Okay, and basically this delta B is equal to the MB prime. These are what we're looking for here. Okay, so basically that's all you need to know from this huge 80 slide PowerPoint. We're not going to worry about the other stuff. We're just going to keep it at conjugate beam method. And during our final review, I will answer questions about this and go over it in more detail if you guys need more help.